In this video, we're going to go over the answer key for the worksheet Acid-Base Concepts number 2. This is a review for your acid-base unit test. The first question asks us for the conjugate for a given acid or the conjugate for a different base. If you recall the definition of an acid according to Bronsted and Lowry, it donates hydrogen ions. So this is nitric acid, HNO3. If it donates this hydrogen ion, what will be left is the conjugate base. So take away a hydrogen and you're left with NO3 instead of HNO3. But since this acid was neutral and it just lost H positive, it just gave away a hydrogen ion, what's left behind now has to be negative. Okay? If you were neutral and you lost a positive, you're now negative. The second question shows us a base, and this base is a derivative of ammonia. Ammonia, we remember, is NH3, and so this thing, when I see NH2 in it, reminds me of ammonia. And bases accept hydrogen ions, so this is going to take on another hydrogen ion. The hydrogen ion will attach to the nitrogen, so we're going to get CH3, and then instead of NH2, NH3. And again, because the hydrogen is positive, and we're now adding it to a neutral substance, this conjugate acid is positive. So the conjugate base is simply whatever's left from your acid after you've lost a hydrogen. So to go from the acid to the base, you just lose H+. To go from the base back to its conjugate acid, you do the reverse. You add hydrogen ions, and that's because of the Bronsted-Lowry definitions. So the third example is acetic acid, CH3COOH, and we remember that hydrogens bonded to carbon are not acidic. Water won't be attracted to those because there's no polarity in those bonds. But the hydrogen bonded to oxygen, that bond is polar, so this hydrogen will be attracted to water. This is the hydrogen that gets donated. So after donating, we'll be left with CH3COO-. The acetate ion is the conjugate base of acetic acid. Carbonate, CO3 2-, is going to take on one hydrogen. Even though its charge is 2-, it will accept one hydrogen, and then later it will accept another one. So if we're looking for the conjugate acid, we just add one hydrogen to that, and we get HCO3. And since it was 2-, the charge will go up by 1 until it becomes 1-, HCO3-. The second question is more of a calculation-based problem. We were given that a solution has a concentration of 0.0052 molar hydroxide ions at 25 degrees Celsius, and we're trying to find the hydronium concentration, the pH, and the pOH. There's more than one way to do this problem. If I have the hydroxide concentration, perhaps I'll start by finding the pOH. pOH is the negative logarithm of the hydroxide concentration. So negative logarithm of 0.0052. Grabbing a calculator, negative log of 0.0052 is 2.28. Remember with your significant digits, since the concentration had two significant digits, the pOH has to have two decimal places. The number in front of the decimal in a pH or a pOH is not considered a significant digit, so only the decimal places in a pH or pOH are significant. Now that we've got the pOH, it's very easy to find the pH. You know that 25 degrees pH plus pOH has to equal 14.00. The 14 comes from the pKW. kW at 25 degrees is 1.0 times 10 to the minus 14. And if you take the negative log of that, you get 14.00. So the pH will just be 14 minus the pOH. for 14 minus 2.28, which is going to be 11.72. Now this makes sense because with such a high concentration of hydroxide ions, this solution had to be basic, and it's basic consistent with that has a high pH and therefore a low pOH. The hydronium concentration we could do in two different ways. We could either use the Kw expression. We know that the Kw, 1.0 times 10 to the minus 14, has to equal the hydronium concentration times the hydroxide ion concentration. So if I know the hydroxide, I can simply take the Kw and divide by that to get the hydronium. Alternatively, we can use the pH here, 11.72, and we could simply say that the concentration of the hydronium is 10 to the power of negative pH. This is the inverse of the pH equation, which is 10 to the power of negative 11.72. Grabbing a calculator, we go second function logarithm to get 10 to the power of, and then negative 11.72 equals 1.9 times 10 to the minus 12. 1.9 times 10 to the minus 12. Because this is a concentration, it needs units, so we'll put molarity beside there. Now just to prove that the other method also works, we could also have said that the hydronium, using the original equation, the Kw expression, is 1.0 times 10 to the minus 14 divided by the hydroxide concentration, 0.0052, and we should get an answer pretty much the same. So 1 times 10 to the minus 14 divided by 0.0052 is 1.9 times 10 to the minus 12. So either method of calculating it will work. Question 3 is a little bit of a word problem. We have a weak monoprotic acid, monoprotic, so this acid has one hydrogen ion to donate, and we're using a generic formula for the acid, just HA, where A stands for acid. Okay, that's not an element on the periodic table, so just HA, an acid with one hydrogen, monoprotic. We're told that it's weak, so it doesn't dissociate completely. This 0.025 molar solution has a pH of 4.35 at 25 degrees Celsius. What's the Ka for the acid? So to do this, I'll start by writing a balanced equation. There's more than one way to start the problem, but HA plus water, weak acids react with water like this when they're dissolved in water. The acid donates hydrogen to the water, so the water becomes hydronium, H3O positive, and you're left with the conjugate base of your acid, which in this case would be A minus. So there's a balanced equation. We had a 0.025 molar solution. The water, I'm setting up here an ice table. The water is a liquid. If you were to put phases, the acid and the two ions are aqueous. The water is liquid, so I'm going to omit it in my ice table. It's not going to be part of the equilibrium expression. Initially, before the acid ionizes, there is a tiny bit of hydronium in pure water. Remember that water has a pH of 7. Kw is 1 times 10 to the minus 14, and so there's that 1 times 10 to the minus 7 molarity hydronium that's present in water at 25 degrees. But that's so small that we almost always will simply ignore it and say that there's no hydronium initially. There's definitely no A minus in the water before the acid ionizes. Now, because it's a weak acid, we would normally just fill in minus X plus X, and some people like to do that anyways, and that's fine, but I prefer to do this. We were told the pH was 4.35, so if we go off to the side of our ice table, we can calculate what the hydronium concentration was in this solution. It's 10 to the minus pH, 10 to the minus 4.35. So with my calculator again, using the second function log button, second function log, 10 to the power of negative 4.35. The hydronium was 4.5 times 10 to the minus 5 molarity. That concentration of hydronium came from the pH, so it goes on the equilibrium line of this table, 4.5 times 10 to the minus 5 molarity. Now we can fill in the table like we would have done back in the equilibrium unit. If you began with nothing for hydronium and now you have this, you must have increased by 4.5 times 10 to the minus 5. The ratios are 1 to 1 to 1, so the A minus also increased by that. They're on the same side of the equation. And the HA must have lost that much. It's on the other side of the equation, so instead of gaining, it's losing. And now if we grab the calculator and subtracted this, we're going to get a number very, very close to 0.025. If we go 0.025 minus 4.5 times 10 to the minus 5, 0.024955. If you want to put that down here, that's fine. Otherwise, you could simply round that off again and say that it's still essentially 0.025 molarity. The A minus, 4.5 times 10 to the minus 5 molarity. So these are concentrations. Now we're trying to find the Ka, calculate the value of Ka for the acid. So we'll write the Ka expression. It's the concentration of the hydronium times A minus concentration over the HA concentration. Now, for those students who filled in this ice table because they saw weak acid and then sort of by reflex wrote minus x, and down here 0.025 take away x, and x, that's fine, and they can even put all that into their expression here. Then they might go off to the side and do what we did here with the hydronium concentration, and they would take this number and put it into that expression where it said x. And then they're going to get basically the same answer that we're getting with this approach here. So they're very similar approaches. We're going to plug these numbers in, so 4.5 times 10 to the minus 5 squared over 0.025. So with your calculator, 4.5 times 10 to the minus 5 squared and divided by 0.025. 8.1 times 10 to the minus 8. There's the value of the Ka for this weak acid. It's a small Ka, which makes sense because the acid was weak. Alright, on the reverse side, we see a sulfuric acid problem. And this is one that has two steps in its ionization and its dissociation. The first step, we remember if we look on a Ka chart, the Ka for step 1 of sulfuric acid's dissociation is large. So H2SO4 is a strong acid because its Ka is large. But when you look up the Ka value for HSO4 minus, which is the conjugate base of that, this will be Ka for step 2, it's not large. It's 0.012 or 0.013 in some books. So we're going to set up two ice tables. The first one will be with Ka1 being large. The second one will be with Ka2, which is small. So let's write the balanced equation. H2SO4 reacts with water. The acid donates hydrogen to water, so we get hydronium ions. And the conjugate base, which is HSO4 minus. We put in an X under water. We can ignore the initial hydronium that's in water because it's so small. Then we get 0.012 molarity and 0 initially. This is a strong acid, so it's 100% ionized. If it's 100% ionized, then it will lose everything that it had. So minus 0.012 plus 0.012 plus 0.012. So you're left with nothing. There's no H2SO4 in the water. there's 0.012 molar hydronium, and there's 0.012 molar HSO4 minus after the first step. Now we recognize that HSO4 minus is actually amphoteric. In this reaction, it's behaving as a base, but it still has this hydrogen, so in our second step, it's going to behave as an acid. HSO4 minus reacts with water, and as an acid, it gives away another hydrogen. So this time we get another hydronium, and the conjugate base of HSO4 minus will be just SO4 2 minus. Because this guy has no more hydrogens, this conjugate base, this is not amphoteric. It's now just a base, and we know that we're done. There's not going to be a third step. The initial HSO4 minus concentration at the start of the second step is the final HSO4 minus concentration at the end of the first step, so 0.012 molarity. The water, like before, can be ignored. The hydronium, though, in the first step, we were putting this acid in water, and we ignored the little tiny bit of hydronium in water. Water has 1 × 10⁻⁷ molarity hydronium, which leads to its pH being 7. But at the end of step 1, we actually have 0.012 molar hydronium already produced. So when step 2 begins, you have this initial 0.012 molar hydronium. There is no sulfate at the end of step 1, so that's a 0. Now in the second ice table, we realize we're dealing with a weak acid. We know it's weak because its Ka was 0.012. So not a large Ka value. So therefore it is not 100% ionized. If it's not 100% ionized, then it does not lose everything, so it's going to lose X, some unknown amount. On the other side of the equation, we'll gain the same amount because the ratios are 1 to 1 to 1. Remember that the change line of an ice table is always based on the ratios in the balanced equations. So at equilibrium, we have 0.012 take away X, we have 0.012 plus X, and we have X for sulfate. If we now go off and set up the Ka expression for step 2, we get Ka2 is 0.012, which is equal to concentration of hydronium times sulfate over HSO4 minus. So 0.012 equals 0.012 plus X times X over 0.012 minus X. Now I'm going to use the solver on my graphing calculator to solve this equation because this concentration of acids that we had 0.012 molar is so low that the assumption method fails with this example. So we're going to have to use the solver on a calculator to do this. On a test, I would not give you a question where the assumption method doesn't work, the approximation method. So with your calculator, if you have a graphing calculator, press the math button, scroll down to option 0, which is the solver. And if you've used it before, just go up, press the up arrow, and clear whatever equation was there before. So we're going to enter this equation in the form 0 equals, which is what the calculator wants. So I'm going to take my 0.012, which is here on the left side of this equation, and I'm going to just move it to the right-hand side when I type it in on my calculator. So it'll become minus 0.012 at the end. So using brackets, let's type in our equation, 0.012 plus X, close that bracket, times that by another X in brackets there, and then divide by another bracket, 0.012 take away X, and close that bracket. And now don't forget to subtract the 0.012 Ka value. There we go, there's the equation, press enter. We're going to give an estimate that our answer is going to be pretty small, therefore pretty close to 0. So I'm going to say that the answer is close to 0, so X equals 0 is my guess, and then I'm going to say alpha solve. So there's the answer. So X equals 0.004 0.497 or 0.0050 molarity, and that's using the solver on my graphing calculator. So now that we've got the value of x, we can say the concentration of hydronium is, looking at step 2, it was 0.012 plus x. So we're going to say here 0.012 plus 0.0050, which means we get 0.017 molarity. And now the pH is negative log of the hydronium, negative log of 0.017, which is negative logarithm 0.017, 1.77. And it makes sense that it's such a low pH for two reasons. Sulfuric acid is a strong acid, diprotic, and it was a reasonably concentrated solution, 0.012 molar, so it's going to have a pretty low pH. Some quick definitions. We've already talked about this, but a Bronsted-Lowry definition of an acid is a substance that donates H plus hydrogen ions in a reaction. So if you see something donating hydrogen ions, that substance is an acid. An electrolyte is a substance that ionizes in water. We'll say water more generally in some liquid, in a solvent, but in this unit we're always talking about water as our solvent, so we'll say that ionizes in water, producing ions. That's what ionized means, so this is a little redundant. Producing ions that allows the water to conduct electricity. It's called an electrolyte because it produces ions in water. Those ions allow the water to conduct electricity. Pure water is not by itself a good conductor of electricity because there's very, very few ions in water. There's just that 1 times 10 to the minus 7 molar hydronium and 1 times 10 to the minus 7 molar hydroxide. So water is not able to conduct electricity very well. If you dissolve an acid or a base or a salt in the water, you'll get lots of ions produced, and then the solution will conduct electricity. The stronger the acid, the stronger the base, the more ions will be produced, and the better the electrolyte will be. A neutral solution. If you're asked to define a neutral solution, try to avoid referring to pH unless you're going to specify a temperature. Some people want to say the pH is 7. That's only true at 25 degrees Celsius. A better definition that's true at any temperature is a solution where the concentration of hydronium ions is equal to the concentration of hydroxide ions, and that's true at any temperature. Now some quick fill in the blanks. 25 degrees Celsius, if you have a solution with pH 5, it's considered, and we've got choices here on the right, the best choice there would be that it's considered acidic. Right? If you're at 25 degrees Celsius, your pH is 5, that's less than 7, therefore that's going to be acidic. This solution has 1%, so it has less hydronium than another solution, with pH equal to what? So the other solution has to have more hydronium than ours. That means it has to be more acidic, and that means it has to have a lower pH. How much lower? Well, because of this number 1%, which is 1 over 100, 100 is 10 squared, 1 over 10 squared, it means there's going to be 2 units of pH difference between these two solutions. For every unit of pH difference, there's a factor of 10 difference in concentration of hydronium. So if we had a pH of 4, another solution with pH 4, our solution would have 1/10 of the hydronium of that solution. pH 3 would have, our solution would be 1/100th of the hydronium in a solution of pH 3. The pH 3 would have more hydronium than ours, so our solution would have 1% or 1/100th of that. So this is going to be 3.0. So there had to be 2 units difference. That's where there was 1%, and the pH is lower than ours because the other solution has more hydronium. Ours has 1%, so ours has less hydronium than the other one. An example of a household acid, there's lots of examples, but from this list the best choice would be vinegar. Vinegar contains acetic acid dissolved in water. HCl, we want to know the pH of a 0.01 molar solution. HCl is a strong acid, so it ionizes completely. In this solution there will be 0.01 molar hydronium ions. And so just doing some mental math or grabbing a calculator, the pH will be 2.00. There were 2 significant digits in the concentration, so I'm keeping 2 decimals in my pH. Strong acids ionize, and from this choice here, this list, ionize completely because it has a large value for its ionization constant, Ka. In our labs with acid-base titrations, we remember using phenolphthalein. It was the acid-base indicator, meaning that it itself is a weak acid where its acid form is one color and its conjugate base form is a different color. It changes color in solution when the pH is very close to the pKa value for the acid. For phenolphthalein, the pKa value is up around 8.5, so below 8.5 pH it's one color, above 8.5 pH it's another color. In our lab, we remember starting off every titration with acid dissolved in our flasks. And when we had the acid dissolved and we added the indicator, it remained colorless. So in an acid solution, it would appear colorless. When we then added sodium hydroxide from our burettes, sodium hydroxide is a strong base, the pH had to go up, and eventually, when we had neutralized all the acid, the pH was now going to be basic because we were adding sodium hydroxide. It turned pink. So in a base solution, phenolphthalein must be pink. If we think of phenolphthalein as a weak acid, HIN might be a generic formula because it's an indicator with one hydrogen ion, monoprotic. Its conjugate base form is IN-. We could say then that the acid form, HIN, is colorless, while the base form, IN-, is pink. So there's the 2 colors for phenolphthalein. If this were litmus, litmus changes color at pH 7, and below that, its acid form is pink, and litmus's basic form is blue. Middle school or elementary school students know that litmus can be used to test for acids and bases. Pink litmus paper turns blue in a base, and blue litmus paper turns pink in an acid. So there you go. There's a nice little review summary of several concepts in our acid-base unit. The second part of the unit deals with bases and salt solutions.